So, good morning. Third lecture of quantitative big imaging. And today I'm going to talk about image enhancement. And no, it's not. So, now it works. So, we have images, and unfortunately, they are not perfect. There are some kind of distortions, there can be noise, and to handle that, we use different kinds of filters. We're going to look at the Fourier transform, some more advanced filters, the structure tensor, and in the end, also some evaluation about how good is your filtering performance and what do you actually do with using your filter. There is a couple of books. One is Jene, Digital Image Processing. Gives you a good introduction to many filter types. It's a bit more technical than John Ross, who, as usually, more show the principle of what things are and a slight hint of theory, but you get nice pictures showing what is before and what is after. For running this notebook or presentation, you need to run these import these modules, quite a bunch this time. Just to mention some, we probably already know the top ones here, but now we're going to use a lot from scikit image and also from scipy ND image. And these will be actually the main libraries that we will work with throughout the whole course actually. It's a quite large, well elaborated package for image processing. Right now I'm mainly using the filters part of it, but it has a lot for segmentation, for morphology, which I'm actually going to talk about more next lecture. And yeah, I think that is all we need to know about the modules. So, as I said before, images that we measure are rarely perfect. There is at least some kind of perception does due to the image. So, if we make an image of a perfect disk, as perfect as you can get it, the imaging system is not able to actually capture that. So what is happening, you will have some blurring, and due to the electronics and to the method you are using to capture the images, you can get some noise, you can get uncorrelated noise, and you can get some textured noise, and this will then corrupt your image in some way. Then if you do tomography, for example, you will see ring artifacts, which are barely visible in this light. And you can also see some line artifacts. And in the end, instead of measuring this very clear image, what you get is this thingy. And it has a lot of noise, it has ring artifacts, it has line artifacts, everything. And that is what you actually can expect when you do an image with some kind of system. So the rings and lines, they are more specific to tomography, but you can have speckles, you can have extreme outliers, and things like that too. So the factors that affect the image quality are, first of all, the resolution, which you at all can resolve, and it also includes the imaging system transfer function. So you always have some degree of blurring. And the blurring should actually be on a scale that is larger than your sampling. Then we have the noise. Another thing is contrast. What if you don't have sufficient contrast? In the medical imaging case, we can talk about different types of tissues. Can you distinguish between adipose tissue and maybe the lung or maybe some muscles, cartilage, whatever. So there you have a very compact range of gray levels that actually include all of these. And then you get the bones, which are far away, and implants, which are even more far away, because they are of metal and usually do some kind of X-ray imaging. With ultrasound, you get different, and MRI, you also get different responses. Another thing is that you could also even have inhomogeneous contrast, which means, depending on your imaging system, if it's corrected or not corrected, you can have one region which is brighter and one region which is darker. And on top of that, we have all the artifacts. In a typical image processing chain, you have your acquisition, then you do some enhancement, which is today's lecture, and then you do segmentation to identify different regions. And for that, you see it's a lot of... You do some evaluation about the metrics you actually want to measure. And noise and artifacts, I already mentioned them, but a very general description of noise, unwanted information. If you talk to someone in a large room and a lot of people are talking, you hear a lot of voices, but you don't want to hear them. So that's a kind of a noise for you in that case. This is a very general description, but normally we're talking about random contributions that obscure our image information. So let's look at what kind of noise we have. We can categorize them in different types. We have completely uncorrelated noise. Each pixel is described by its own noise distribution. Usually it's the same distribution, but it's a realization of the same noise distribution. And typical noise that we are approaching is the Gaussian noise. It's very easy to model, and that's why it's so popular to work with. Then we have salt and pepper noise, and that is a kind of outlier noise. It can be from, well, only just black and white, but it can also be some kind of amplitudes in it, and sometimes it even goes below the image intensity. But in principle, we are talking about random distribution of outliers. And it doesn't have to always be just single pixels, it can also be small clusters, then we're more talking about speckle. Then finally, we also have structured noise, which has some kind of spatial dependency. It depends on its neighbors. And that is what you may get if you work with a maybe not so homogeneous syntax transformation device from the radiation type to visible light. And with that, it's not completely inhomogeneous. Could be from a manufacturing principle, or even that it's not possible to get a homogeneous distribution of the fluorescent particles. And then you can get something like this. So you can actually get all of these in combination in your images. And looking at the Gaussian noise, you probably have seen it a couple of times already, the distribution of it in your math and statistics classes. So what we have is we have an average value, and that describes the intensity. And then we have a standard deviation, which describes the width of this. And one distribution that is actually very important when you're talking about imaging, because we're talking about is the Poisson distribution, and that one is always really important when you have counting statistics in your acquisition. And in imaging, we are counting photons from light or X-rays. We may be counting neutrons, photons, protons, whatever. Everybody of these are described describe the noise using the Poisson distribution. And very specific with this one is that is intensity dependent. So the distribution width is changing with the number of counts you get. It is also, for few counts, asymmetric. The Gaussian curve was a nice symmetric bell. The Poisson noise is skewed towards lower values. Unfortunately, it doesn't show up so well on the screen here now, but okay, there it is. So here you can see that it has more weights or more number of counts for the low values, and then it goes out in a tail. Yes?
Those values are the signal to noise ratio.
I'm coming to signal to noise ratio. It's not the signal to noise ratio. So, anyway, if you add the number of counts, the shape of this curve will move more and more to look like a Gaussian. That's why the Gaussian is so popular also to use. But the correct model is actually the Poisson. And here you can see the effect. I tried to make some Gaussian noise plots around the sine curve. And you can see there is a uniform distribution no matter what amplitude we have of the sine. But with the Poisson noise, there is a large amplitude at the highest amplitude of the sine, and it narrowing down around the lower amplitude. And if I extract that, you can see, hopefully see that there is more or less a straight line or straight distribution here, but here it narrows down at the lower amplitude. The salt and pepper noise is the outlier noise. Typically, you describe it as you have a uniform distribution of some random variable. If the random variable is a value, then we set the -1. If it's a value, then we set it as 1, and in between we have just zeros. And the lambda 1 plus lambda 2 is the noise fraction in this salt and pepper noise. And here we have some the dark that, whoops, and 5%, and then we have the snowstorm, 10% of each. This is still not too bad. It can actually be filtered when it's like this. And now we come to the signal to noise ratio actually. And the signal to noise ratio is defined as the average intensity in a region divided by the standard deviation. And if we look at signal to noise ratio for Poisson noise, which is a very specific, is that if we take the average value of the Poisson distribution, we get an n, which is the count. And if we take the standard deviation, it's a square root of n. So for Poisson noise, you have the relation for signal to noise ratio that it's the square root of the number of counts. This means to double the signal to noise ratio in an image, you actually need to measure 4 times more counts. And here you see an example nicely from real measurements. I did it with neutrons in this case. Here I did a 50 millisecond exposure. You can see it's quite noisy, and the signal to noise ratio is below 10. Then when I expose it at 10 seconds, then it's much, much cleaner, and we have a signal to noise ratio of 70. So this shows a little bit how, and then it also, you can see nicely that it follows the square root of n. To generate noise, sometimes you actually want to generate noise. For testing purposes, then we have some Python functions, which I list here. And if you want to compute the statistics, you can compute the average value, variance, standard deviation. Can also look for the mean and maximum. Median can also be computed in the same way. And yeah, so this is a collection of useful functions that you can use. And there we have the median and rank. The rank is when you sort all the values in the data, then you can select one fraction of it or 1 point of it. So the rank of the half number is the same as the median. And the rank 0 is the same as minimum, and rank last element is the maximum value. So it's a collective function for all of these three. So we now know that we have noise, and now we want to get rid of it. So let's start talking about basic filtering. And first of all, what is a filter? In principle, it is some kind of processing unit, a piece of program. In electronics, it would probably be some kind of network of capacitors and coils. But here we are talking about, in principle, about a unit that enhances the wanted information and suppresses the unwanted information. And that's not it. But usually we have a trade-off between how much we destroy using the filter and how much we take out. So sometimes you can use a filter that actually takes out all the information. You just have a flat image. That's a little bit too much, and that we don't want. We have different filter characteristics depending on what frequency they address, and actually that also tells us which information we can extract from the image. The first type is a low-pass filter, and the low-pass filter looks at the lower frequencies, spatial frequencies in the image, and enhances them while it actually suppresses the higher frequencies. The effect is that all the rapid changes, they are removed, while the slow changes are still there. So that means with a low-pass filter, you can take out the noise. Here's a little bit schematic example where you have these rapid changes and some slow changes, and after the low-pass filter, you should ideally get something like this. The opposite is a high-pass filter, and now we try to remove everything about low frequencies, so slow variations, and enhance the fast variations. So that would in principle be that we enhance the noise. But another thing is that rapid changes in the image are actually also edges. And this is what is going to be enhanced with a high-pass filter. I will show that in more detail later. So some filters. Typically, when we start out using filters, we use linear filters, and they are computed using the convolution. And the convolution can be done in any dimension, if you like. In the typical math courses, you probably only do it in one dimension, but it works as fine in 2D and 3D as well. And here we have the image, and it's run through some convolution kernel, and afterwards we have the convolution, the point spread function of the kernel convolve the image itself. So looking at some filter kernels, there are some classic kernels that are used a lot in image processing. The first one is very simple, is the mean or box filter, and also called uniform filter. So it has many names because it's so popular to use and comes also in different applications. But in principle, what it is a kernel that weights in the convolution have the same value. And typically you have ones, or actually 1 over the number of elements in the kernel, and then you have that in each element. Oops. And Another very popular kernel is the Gauss filter. Has a maximum value and then it tapers off, so it focuses on central information around the central pixel in when you do the convolution. And as I said before, let's see, there it is. Low-pass filter, they suppress noise in images. And of course, this one gives a more averaging effect, but it can also introduce some kind of unwanted artifacts in the filtering. This is less because it's, first of all, it has a round shape, and also that it tapers off towards the edges. So what does it do when we apply a Gauss filter to different signal-to-noise ratio? First, I have the image itself, more or less, very high signal-to-noise ratio. So this is an image, very clean. Then we decrease the signal-to-noise ratio. We see that's getting a bit noisy. We decrease it even more. So now it's getting hard to even see anything. And on the last one, you can barely see the contours of the picture we have here. And if we now apply a Gaussian filter to that with a sigma equal 1, you see that in this case, not much change. Maybe you can start seeing that some of the features are a bit blurred. Actually already blurred out. And so on a clean image, it's no good idea to actually apply a Gauss filter. If you start now to decrease the signal-to-noise ratio and apply the filter, you can see that there is a great improvement, because this one was a bit noisier, and this one starts looking more or less like the other one. So that's what's a good choice. And when we go on with the lower signal-to-noise ratio, you see that you actually can extract a little bit more from these images. And if we go to the worst case, then of course the blurring is destroying essentially all information. You can just see the contours. But the effect is at least that you have no noise anymore. So you could, as a minimum, be able to identify, have it at least. And sometimes that is what you have to be satisfied with, in particular if you have that kind of very noisy images. So you have to know a little bit how the signal-to-noise ratio and the filter kernel are hang together, and when you should use and not using a strong filtering. The convolution is very simplified. How it works is if you have this box filter kernel, what you do is essentially when it's computed, and I don't say you have to implement it because it's implemented by many people before, but if you want to do it for your own understanding, you are allowed to, of course. But what it's doing is taking the central pixel and a neighborhood around it, and that is summed up, and then you divide it, in this case, by 9, because we have 9 elements, and then you get some average value, which you're putting back in the filtered image. One thing that I don't think I have a slide about is usually when you choose the filter kernel, use an odd number, because if you use an even number, then you will introduce a shift in your resulting image. Sometimes the even number filtering is even using the corner pixel as the starting point, and then you shift a lot, a little bit diagonally, a lot down. Sometimes it's trying to do one of the mid pixels, but that is also a shift by 1 pixel. So the best choice is actually to always use an odd numbered convolution kernel. One interesting thing, a mathematical detail about convolution, is that sometimes you can combine filters, and we have the associative and commutative laws that apply to the convolution. So what we can see is image A convolved by B and then by C is the same as A convolved by the convolution of B and C. We can also flip the order, and this is very helpful because you can reduce the computational effort needed. And there are a couple of kernels that you can actually split up like this. And looking at the box, you can actually split it up into two kernels. So if you have a 9 by 9, then you can split it into a 1 by 3 and 3 by 1 and 1 by 3, and can apply those two as ones. The Gauss filter, same way, can also be split up into one component in the x direction and one component in the y direction. Now you may ask yourself, is this really a good idea? Sometimes yes. If you have large kernels, you have a kernel which is 15 by 15 large, then you have quite many operations to do in one case. So, or if you have three-dimensional filtering, then really a big change, because say you have just a 5 by 5 by 5 filter kernel. That would be 125 multiplications and 124 additions. And if you split it down instead, you would have 15 multiplications and, let's see now, 12 additions. So that is a huge win numerically. And sometimes it's a good thing, but you have actually to test it with your system, what is faster, to actually take the big kernel or doing it in a separated way, because there is also a call overhead when you call these functions, and depending on programming language and how it's implemented, sometimes this overhead costs more than the gain you do with the numerical improvement. So that is something you have to try out. But there is a potential of doing speed-up gains by doing this. Yeah, here comes an example, as I did it more difficult before with the 5 by 5. One thing I want to mention is if you go look at the slides, you don't see all information in these notebooks, because I have usually added notes where I describe a little bit more around the slide. So there is more reading material if you look into the notebooks instead of on the slides. The median filter is not a linear filter. It's actually applying the median to a local neighborhood, though it still has a low-pass filtering effect. And looking at what we're doing in the median filter is we take, again, this neighborhood, again, preferably odd-sized. We sort all the elements, and then we select the mid-value as we do with the median, and that value is placed on the resulting image. So why doing this? It's actually computationally more doing the convolution, but it has the advantage it's very good against outliers. And looking at a very spotty image, so this is a grasshopper, and I have added now a lot of spots, as you can see. If we apply a Gauss filter on that, you can see that, okay, it reduces the effect a little, but it doesn't do that good to remove these spots. If we apply the median filter instead, you can see it's a very clean image that comes out. Now with the current light conditions, it's hard to see, but if you would have Gaussian noise and apply a Gauss filter or median filter, the effect is more or less the same. I think the Gauss filter would probably perform better in removing this noise. But so now is the question when to use which. Another thing is that the medium filter is also more gentle to edges, and that makes it also very popular in to use as a denoising filter. I'm usually personally hesitating on using the Gaussian filter, medium filter, sorry, because it is actually destroying the statistical distribution behind the data, and it's also only a selection, and that gives you probably more or less the same distribution, but not exactly the same. So if you want to do some true statistical analysis based on the gray levels afterwards, it could be that the medium filtered image will perform less good. One example where the medium filter comes in well is spot cleaning. So in many imaging techniques, you may get these outlier spots. It could be that it's detector faults. It could be, as with the neutrons, it's actually part of the physical process interaction between matter and neutrons that generate gamma photons that hit the detector, and then we have a lot of these spots. And they need to be removed, otherwise you will have a lot of line filters in line artifacts in the resulting tomography. So what we should do to remove these, one is to just apply a low-pass filter, but we saw before on the grasshopper that the low-pass filter doesn't really do a good job in removing outliers. We could apply a medium filter, but that would, in principle, smooth the whole image, which we don't want. We don't want to lose image sharpness just because we take out these spots. And the approach I'm going to show you on the next slide is to detect the spots and then to replace them by some estimate of what it could be behind. The algorithm that can be used is that we start with our original image, which is medium filtered. Then we get this smooth image with some kernel size. The size depends on the size of the spots. And then you subtract that one from the original and take the absolute. And from there we can detect if we have outliers, because in the difference image, the outliers would appear as very, very sharp, and the structures hopefully in the image. And by this selection, you can take all the outliers and compute a replacement, which is based on the median. And otherwise, you take the image as it was, and then out comes the. And this is quite efficient for many cases. There are better algorithms, but this one is a good starting point to replace the median with. And just to look at what happens if you have the image. Here we have the original with some spots here, and here are 3 in this cluster here. And if you just apply the box filter, you will see that it's still like an island here, caused by this little line-like outlier. Here you get really truly a box, and also here you get some ugliness. With the filter, you remove all the spots, and you can also see some blurring of the image, so you actually lose information by applying this. And when we now use this cleaning algorithm, you have all the sharpness preserved and the spots are gone. So looking at the differences between original and box, median and the difference cleaning, you can see here the improvement in image quality from this process. For those who use ImageJ, it's a quite popular interactive program to image analysis. There are different ways to do outlier removal, and they call it with a nice name, but there is one called despeckle, which is plain simple median, so don't use that to remove outliers. And then there is this remove outliers in the very same menu. And that is more or less the algorithm that I described here. What you need to do, specify here, is the size of the area you want to detect and a threshold. And with that, and also you have to say if you want the dark or the bright outliers. So, leaving low-pass filters, actually the spots was kind of a transition. Now we switch over to looking at high-pass filters, and these filters, they instead enhance the rapid changes, and we can use them for edge detection. And typical high-pass filters are gradients. So, very simple numerical gradient is just that you take the neighbor elements, subtract the previous one from the current one, and then you get your gradient. A more exact one, which is more orientation true, is to use this kind of kernel, which is described by Jene in the book I mentioned in references. And another one would be also to work with the Laplacian, which has this filter shape. So you can see that you have the average of the surrounding minus the center pixel. And this one then computes the Laplacian, and you will soon see the effect of these. Another one, which is also very popular in edge detection, is the Sobel filter, which is the magnitude of the gradient. And let's see now what they do. First of all, we have, let's see, I realize I don't have maximized my window. So, then we see a little bit more. And now we have the vertical and horizontal edges defined as by Jene. And we can see the effect of it, again with the light today. Oops. We may not see all the structures, but I hope you can see it on your... So we have the original here. It's a piece of a diesel particulate filter with some soot and ash. And when you do the derivative in x, you can see the vertical lines. If you do the derivative in y, you can see the horizontal lines. And if you look really close, you can see that there is one dark and one bright. And with that, you can see falling and rising edges. Because in one case, the derivative is positive, and the other case, it's negative. Then we can also use these filters to detect edges. And the two popular ones are to use the Laplacian or the... And the Laplacian has the effect that it has positive and negative values. As you can see here, when you come from the dark parts going into the bright, then you have first a negative value and then you have a positive value. So it's first going down and then up and then onto the flat area. The Sobel filter only shows the magnitude, so it always has positive values. And depending on which kind of detection you want to do, you can select either the one or the other. So in some cases, you can even use the positive-negative effect and look for the sign change and use that as the indication where you have the edge. In this case, you have to look for the maximum instead. And these filters, they can be used in many applications, and nowadays with machine learning for image processing, it's actually a big bunch of convolution kernels. So we are talking about convolutional networks, and the different features are extracted by filter kernels that have been optimized to produce the answers from the trained data. So it's when you train a convolutional network, it's for one thing, it's adding a lot of convolution kernels, Some cases you have fixed kernels, other cases actually trained to take different shapes. And then combine them with a cross network of weights to produce the next image. And this case was about finding the speed limit on traffic signs. And well, it goes through the network, and this is an example that was provided from NVIDIA. So it's probably using the CUDA network for doing this training task. So I think, well, let's take this one too. Frequency space. I have already talked about frequencies, that we have slow changes with low frequencies, we have fast changes with higher frequencies, and we can actually also apply our filters in frequency space. And for that, we need to use the Fourier transform in 2 dimensions. Sometimes also in 3 dimensions, but usually it's applied in the 2 dimensions. So what we have is these 2 equations where we have the Fourier transform going from spatial domain to reciprocal domain, and the reverse transform that brings you back, and that without any. And these equations, for the daily work with images, you don't really need to know them, but because it's implemented, people have done even the fast Fourier transform, because computing the Fourier transform, if you do the discrete transform as it is, defined by the equations, then you would have a complexity of n squared, which is a lot. But with a fast Fourier transform, you can do n log n, and then you speed it up quite a lot, with some limitations on the shape of the data. And well, the fast Fourier transform is available in multiple variations. You have it in scikit-image, you have it in NumPy, you have it in SciPy. There are even specific libraries applying the fast Fourier transform, so there are plenty of these out there. So, some mathematical features of the Fourier transform. First of all, we have the addition. So if you have the Fourier transform of 2 signals, A and B, it's the same thing as if you have the Fourier transform of signal A plus the Fourier transform of signal B. Looking at the 2 signals, we have a low frequency and a higher frequency signal. And if you add the 2 of them, it looks like this. And in the frequency space, you will have 2 peaks, in this case very narrow to the center frequency. And if you have a faster one, they will move out a little bit from each other. And when you do the Fourier transform of the sum, you can see that now you get 4 peaks where you can easily identify that you have 2 frequencies. That would be harder to identify looking at this one. Other things that are interesting is the convolution. And the convolution in the real space is the same as the multiplication between the 2 signals in a reciprocal space. And that's a very useful thing. The other way around is also working. So if you have a multiplication between 2 signals, then it's the convolution in the Fourier space. That is, however, less used at least for filter purposes. So let's look at some images. We have this image of a couple of balls, and I add noise. So the noisy image looks like this, and this is what we are going to work with. And if we look at the Fourier transform of these, it's maybe not so easy to interpret, but what you have is you have in the middle a very bright spot. That is the DC component, or the very slow variations in the image. And then you usually have some preferential directions in X and Y, and around it you see a cloud of fuzzy stuff, and that is actually the whole image information. The noise well, it looks like noise also in the Fourier space. And if you add the two of them, then you see that the noise actually overrides a bit of these very sharp lines along the major axis, and also you lose some of this information. So that means these parts of the image, they have lower frequency information than the noise itself. One thing to mention here is when you compute the fast Fourier transform, then the frequencies are set so that the positive zero value is at the zero position in the vector, and the negative zero is at the end of the vector. So you have more like a bow like this, and in order to bring the center frequency in the middle, you need to use this FFT shift function. Otherwise, you would have 4 bright corners and nothing in the middle. So, I think we break here, and then I continue with how the convolution works after the break.